My name is Tyshawn Bullock,
My name is Mary Wilson.
and we're going to be presenting the traffic sign recognition model. The abstract, this project presents the design and implementation of a project design traffic design recognition system using deep learning. The goal is to build a model capable of accuracy classifying US systems for traffic signs in real time for image inputs or live webcam feed using MobileNet V2 with transfer learning. The model was trained on a custom data set containing our four key traffic design classes: stop, speed light, no entry, and crosswalk. This system was developed in Python using TensorFlow and OpenVC and includes models for training, prediction, and real-time streaming. I can go to the next slide.
Traffic signs provide critical instructions for drivers, pedestrians, and intelligent systems. Manual recognition of traffic signs can be error-prone, especially in high-speed or poor visibility situations. Automating this process with deep learning improves road safety and efficiency. This project uses computer vision and convolutional neural networks to automatically identify traffic signs from images and video input. A few of our objectives were to build a model capable of recognizing traffic signs with high accuracy, enabling predictions on images and real-time video stream input, and preparing the foundation for integration into embedded or web-based systems, such as a mobile app, in a car, or a website.
The budget plan was the Jetson Nano, which was $99, the USB camera model, which was $25, the micro SD card, which was $12, the cloud GPU time was $50, Manilus was $14, and the total came out to $200. This is the Theory CNN and model, the model Net V2. This is the recognition model. Um, and then you can just go to the next slide.
The theory, data set, and pre-processing, well, so we had four classes, which were stop, speed limit, no entry, and crosswalk. And our image dimensions were 64 by 64. And our rescaling pixel values were normalized to 0, 1. And right here, I have our code for the image handler file, which deals with all the images that are uploaded into the model. And our data set split was 80% training and 20% validation. Our design, our folder and our code structure, basically how we organized the project. In the folder layout, we had the data set and a train folder, which included our four class sets, which were stop, speed limit, no entry, and crosswalk. And then we had our test images folder, which contained all of the images, and our model, our static, and our templates, and our scripts were our files with our code in them.
This is our design, the source code summary. The train model PY builds and trains the mobile net V2 model. The CNN model PY contains a reusable prediction class. The test image PY tests prediction on a single image. The test stream PY predicts from a live webcam stream. The design model interface pipeline that starts from image input, pre-processing, mobile net V2 model, soft max output, prediction label, confidence, the visual overlay, bounding box and label, and then you go to the next slide.
So our results for our model training, this is where we trained the model to incorporate all the images, and basically every time that it runs is where you have your confidence and your validation. So we did 10 epochs, which is one complete pass through the entire training data set, which is shown in this image right here. And this is our code for the to train the model, and we received 95% accuracy on training and 92% accuracy on validation. And here are the results of the test image. So it predicted a image of no entry where there's no stop sign on the road. And it predicted this with 97% confidence and correctly classified the image as no entry.
And then this is the results. This test string PY output. It outputs real-time detection via a webcam. It labels confidence overlaid and on live video feed, responsive and accurate for multiple traffic signs. This is the results. Multi-class detection. Successfully predicted different signs in the live stream. The stop sign with 83%, the speed limit, the no entry, and then this demonstrates the ability to adapt to lighting and position.
So next is discussion and performance and limitations. So our performance had high classification accuracy, real-time frame rate maintained on CPU, and some of our limitations were a small data set. We only used 4 classes for our first data set, and performance may degrade in poor lighting or partial occlusion. And there could also be possible confusion between similar sign shapes. Um, However, the system has a few limitations, but mainly it was able to detect most of the images properly and over 50 to 80% confidence. And our future work, we plan on adding more classes such as yield signs, pedestrian crossing, being more specific, and also turn signs and turn signals and speed limit signs, like incorporating the numbers so that it just doesn't just say speed limit, it'll say speed limit 25 or speed limit 30. And we also are going to incorporate object detection as shown in this image to the left, where it picks up the traffic sign and recognizes it in the frames. And we also plan on extending into UI, a full web app or mobile app, and also deploying it to Jetson Nano. And this is an example of like how it will look on a mobile interface.
All right, this is our project schedule plan. Runs through February through May. In February, the data set creation and planning. In March, the model building and training. April is testing real-time development. And then May is the presentation and final documentation. This is the code for the UI preview.
Here it's predicting a stop sign with over 50% accuracy. And the speed limit sign with 100% accuracy. And the crosswalk sign, which sometimes it could be unsure about it due to the shape, the position. It could pick it up as a stop sign every now and then, but it overall does predict it as a crosswalk sign. In conclusion, this project demonstrates the application of deep learning for real-time traffic sign recognition using MobileNet V2 and a custom data set that we created. We successfully trained a high-performing model and integrated it into a Python-based application. With additional classes and deployment steps, this system can contribute to real-world intelligent transportation systems. And here is a list of our references that we use for this project. And that is all we have. Thank you.